thank you for that. I've been in Cambridge for about 22 years now. That is very un-Cambridge. So I'm really happy to be here tonight. You know, as I said, I've been here for a really long time. I love this city. It is a real hotbed of innovation and people that help each other as well in terms of what they're trying to do with the companies that they have and innovations that they're trying to develop. So what I wanted to do tonight was talk a little bit about the company and our technology, Breath Biopsy, and give you a little bit of a history into it, because I think often you get the nice kind of polished version of what happens when you're trying to build a company. So I want to try and take you behind the scenes a little bit. So at Owlstone, we've developed a breathalyzer for disease, and our company mission is to save 100,000 lives. So we see two big problems in healthcare. The first is too many people are diagnosed with disease when it's too late to cure. And the second is too many people are on medications that don't work for them. And there's no better example than in cancer. We know if you can pick it up sooner, survival chances are 10 times better and treatment costs are 10 times lower. So our goal is to try and pick up chemical markers on breath, which are biomarkers associated with different diseases, including cancer. So we got started back in 2004. So we spun out of Cambridge then. The medical part of the business is actually only about 3.5 years old. And since then, we've grown to a team of 170 people, and we've raised about $90 million of investments. We're based over in the Science Park. And, again, whenever I hear kind of company introductions and snapshots like that, it's always a little bit irritating because it's like, oh yeah, here's this thing and it all looks great. And again, often you don't see that, the behind the polished little gemstone is the fact that you had to dig in the shit for 10 years to find a little rock, and it's the wrong rock, and then you try and keep digging and finding something until you actually have something of value. So this is the kind of polished snapshot. So if we go back a good few years to 2004, so Owlstone was started by myself and two other guys, David and Andrew, these guys here. So we were engineers at the Cambridge Engineering Department, and we were electronics geeks basically, but we had a real interest in trying to start a business. And Andrew was born in the US, went to Caltech, and he got interested in chemical sensing there. So when he came to Cambridge, he was actually pretty canny because as a self-funded PhD student, he would own his IP. So he kind of came saying, I want to try and develop an innovation, but I want to try and start a business off the back of that. And David and me, we were in the same lab together, and we're like, chemical sensing sounds pretty cool, let's get involved with it. But again, technically we knew what we're doing, but had zero commercial experience whatsoever. But we were very fortunate because one of the great things about Cambridge is the very vibrant entrepreneurial community that's here. So we became part of the Cambridge University Entrepreneur Society, entered the business plan competition there, and part of the great thing about that was it gave us access to mentors, people who are willing to give up their time to try and help three clueless engineers put together a business plan and try and navigate how you turn technology into an actual business. So we went through that process, and we had this idea of a better chemical sensor that can pick up very small quantities of chemicals on a silicon chip that you can program just by changing the software. And we thought we knew how we could build this thing. But the problem with hardware is you need quite a lot of money to start with. So we were trying to raise money. And one of the things that we were trying to do was figure out how we could sell the business. So as part of the Entrepreneurship Society, they arranged pitch competitions and pitch training. And this was great. So me and Dave went along to pitch training and said, right, everyone in a circle, Dave was there, I'm over this side. I get up, did my pitch, gets around to Dave, he gets up and did his pitch. So about 20 minutes later, the guy realized that he didn't know we were even from the same company. That was how bad our pitch was at the time. He said, well, hang on, you guys, you're doing the same thing. You guys are terrible. But we persevered. We went through the training, got a little bit better, went out and then pitched our first investor. the thought of it still gives me the cold sweat. It was a disaster from start to finish. And I think, we weren't confident in trying to present the ideas, but equally, as I mentioned, we were technically competent but commercially clueless. I remembered, the investor saying, what's your margin? I'm like, I don't know what margin is. I thought he was talking about the margin, the left margin on the business plan. I'm like, one centimeter? I don't know. And so I was like, okay, I don't know what margin is. I will guess that more of it is good. So I was like, it's good or margin's high. And he kind of nods. It's like, okay, right answer. And then I kind of scuttle off and look it up on Wikipedia what margin actually means. But again, through all these experiences, we were getting better over time. We're figuring it out as we went along. And then we had this wonderful, lucky experience where I was out with some friends, and the college that I went to was Trinity Hall. And Trinity Hall has quite a nice bar now. It didn't back in 2004. It had quite a grim, small but wonderful bar back then. And I'd been out with some friends. We went into the college bar, and the barman introduced me to a guy sitting on this bar stool. He's like, what do you do? And I'm like, I'm an engineer, but me and my friends are really interested in trying to start a business around chemical sensing using nanotechnology. And I'm like, what do you do? He's like, I'm an investor. I invest in nanotechnology companies. I literally had the business plan in my back pocket. So from that chance meeting, we went through a whole due diligence process, and those guys ended up investing the first $2 million in the company. So we were kind of off to the races. We had this idea for a chemical sensor technology. We had the money to try and give it a go. And I think through that kind of early experience, there's a few things that became apparent to us. I think one of them, and this still happens today, so I hear the word no so frequently from investors, customers, whatever, that I fully expected to walk into Starbucks, ask for a coffee, and for them to say, no, sir, sorry, we're not going to do that for you today. But I think the big lesson that we learned was actually sticking through the process is the only way through. So it's never going to work right first time, but being able to keep your head down and keep going was critical for us. The second thing, I live just over a Mill Road, so I kind of cycle from here, past the reality checkpoint. Does everyone know where this is? Yeah, so I think back then, what was great for us was, we wrote this business plan. It's like, this is this wonderful creation here. Most of it's total bullshit, because you don't know. You're guessing about certain things. You're guessing that a customer will want this at this certain price. And I think for us, what we realized was that, we had to get past the reality checkpoint to go out into the marketplace, with investors, with customers, to try and actually test our assumptions. And this was before the whole lean startup thing was in vogue. So I think very much a key component of what we did and what we try to do today is make sure that we don't kid ourselves. Work on the basis that everything that we think is a bit of an assumption, and we need to test those assumptions. So one of the, again, wonderful experiences that we had in the early days and today still is the fact that we are in Cambridge, and that there are so many people here who have done wonderful things, who are willing to give up their time. And we had lots of mentors. So this is Walter Harriet. People like Tim sitting at the back have been fantastically helpful for us in the past. And Walter was great, because when we were trying to close our first $2 million deal, so we were trying to negotiate the valuation. So, we crafted this wonderfully complex spreadsheet, precise to 50 decimal places and stuff like that. And we go into Walter, and he had been giving us lots of fantastic advice up to that point. He's like, Billy, is anyone else offering you money? We're like, no. He's like, well, it's easy. Take that. It doesn't matter what your friggin' spreadsheet says. And I think what was great about the likes of him and others was that practical experience and that willingness to share that experience and share their time with us makes Cambridge a very, very special place. And one of the, I mentioned, we found our first investor by chance. At a bar, we got chatting, and one thing leads to another. You have a $2 million check, it's a little bit annoying to say what you should do is be lucky, because you can't really control that. And there's plenty of other examples of Cambridge companies, and generally where serendipity and luck play a key role. And I think one of the realizations that we still have is that while you can't be lucky per se, what you can do is put yourself in a position for serendipitous things to happen. And I heard a wonderful phrase. I don't know if it's from a Greek philosopher or someone who was pissed down in the pub one time, but it's let your hook always be cast. In the stream where you least expect it, there will be a fish. And I think that's about getting out there, trying to create those opportunities where you can be in environments where you will meet people, where you do have the opportunity to try and create that type of luck. When Simon told me the venue for this place, I was very happy. And I was very happy because it's close to Scudamores. So when I was a student, engineering during term time, and then I'd spend very happy summers out on the bridge there working for Scudamores. And anyone that lives in the town now probably thinks I'm a bit of a pest. You often get pestered by the punt tides. But actually, that job was really fascinating because I was getting the formal education at Cambridge. So learn this about MOSFET transistors and stuff like that. But actually, at Scudamores, it probably taught me one of the most valuable skills, which was how to sell. So we'd be up on the bridge and you had to sell tickets. You didn't get paid for pushing the boats. You only got paid for what you sold. So some days you would leave and you earned nothing. You'd be there for 8 hours and you haven't earned a single penny. And you have to beg your friends to buy you a drink in the Anchor. And then other days you'd have a good day, you might earn 50, 100 pounds, whatever it may be. But the key was you had to get good at selling. That was the thing that paid. And actually, the experience that we've had in business is that sales often is at the heart of everything that you need to do in terms of raising investment, in terms of trying to sell to customers once you have products, but also trying to get people into your team to follow you in what you're doing as well. Ultimately, the ability to sell your idea, I think, is one of the things that makes it possible for those ideas to become reality. So that was kind of early days. We had got our initial funding, which allowed us to develop our chemical sensor technology. So it's called FAMES, and it's a bit like an electronic nose. So you have a mix of chemicals that come through, and what we can do in this chip is apply electric fields in such a way that the smell of interest comes through and gets detected. But what makes it special is that you can program that just in software. So if you want to detect a toxic gas, you change the software for that. If you want to detect a different compound in an industrial application, you can change it for that. And this was the kind of technical experience that we had when we were at Cambridge. So MEMS and microsystems devices. And we had this wonderful idea on paper. We had the funding that we could go to silicon foundries to try and make devices. And man, was it hard. We would send a design away, wait 3-4 months, the chip would come back from the foundry, and it doesn't bloody work. And we don't know why it doesn't work. We'd spend another few £100,000, chips come back, they don't work. Oh, why is this one not working? Oh, it's a different problem that popped up second time round. And I think this was just a fundamental reality of sensor technology, microchip technology, and hardware. The general principle that hardware is hard. and you have a large capital requirement that you don't often have when you're trying to build a software company, and you have these very, very long lead times as well when you're trying to get devices back. But we persevered. We got first devices working after about 18 months or so. There's in our office at the other side of town, there's our very first chemical spectra we ever captured, which it was horrible, but it kind of worked a bit. But right around that time, we're like, okay, we have this technology, it's starting to do something. We need to start trying to find customers here. And in our mind, we were a sensor company. We're going to make sensors. We're going to sell a gazillion into the automotive industry, gazillion into consumer, and we worked hard to get our first sale. And I remember saying to our investors, great news, guys. We've sold something. It's like, what have you sold? It's like, we sold a chip for $100. And they're like, we put in $2 million and you've sold one chip for $100. And I'm like, yeah, but they want to evaluate it, and this could turn into big business down the line. But I think what we realized at that point was that actually, our conception of what the business model was very different from what it needed to be. We were thinking of ourselves as a sensor company, but we realized that we needed to move higher in the value chain. We needed to start building instruments, because we cared more than anyone else about trying to get the technology in their products. And it turns out the customers only just wanted to have their particular problem solved. So in a security application, they wanted to detect the explosive. In an industrial application, they wanted to detect the contamination of crude oil. They didn't want to piss about with the sensor. They just want that problem solved. So we had to move away from just the sensor to trying to build all the systems that go around it, which meant that we needed to grow the team, add disciplines, and additional people that we didn't have before. And the first kind of application that we tackled was around military use. So looking at toxic gases, explosives, and those types of things. And because the technology can program for different things, we thought it's very flexible. We can use it in these different applications. But what we also saw was that, and this was Andrew coming across from the US, that there was a lot of funding that would come in from government agencies around some of the security applications. So we applied for things like SBRI, which is a fantastic scheme in the US and is in the UK now, where essentially the customer's telling you, I have this problem, I need to detect these particular gases, I will fund your technology and product development there. So we won a few of those, and we parlayed those into bigger contracts. And over the years, we actually won about $30 million worth of contracts. And this was great because it was a non-dilutive funding to mature the technology, which we could use in different types of applications. But around 2007, 2008, the kind of economy has a bit of a meltdown, and the challenge of the security type applications was you have a very limited number of customers. Government is your customer, and when they say we're not spending money anymore, you need to think, all right, what do we do now? So I think we had advanced the technology to the point where we started to think about some of the ancillary applications that sit around this. So, out of necessity, we started to look around industrial applications. So again, making product, but high value type applications where you're trying to do things like detect contaminants like methanol and crude oil. So we developed this instrument here called Lone Star, which allows you to sniff things like oil, foodstuffs, and water. And in this part of the business, we're able to sell instruments for quite a lot of money, but it's a very niche business. You could only sell a few, small handful of instruments here and there. But it saved our necks. When the economy wasn't looking good, we were still able to survive and eke out an existence by pivoting to these types of applications. And what we've seen over time is a bit of a resurgence in some of the original security applications. But again, because the technology, you have this general purpose capability to sniff different chemicals, we started to do work with the academic research community as well. So you had clinical researchers who had previously been interested in electronic nose technologies to try and find biomarkers of different diseases in breath and urine and fecal samples and those types of things. So some of these guys are saying, okay, well, we want to try out your technology here as well. We're like, great, we get to sell a product. They weren't too much support. They could kind of get on with stuff themselves. And what was great was these researchers were able to get the system, get patient samples, run them through the device, detect different chemicals, and then they would publish some of the findings here. And as a few of these publications came trickling through, we started to look at this a bit more seriously. So one of the papers that came out was a group up in Warwick who had been looking at the chemicals coming from a urine sample for patients that had colorectal cancer. They're small studies, so you always need to treat them with a pinch of salt and a degree of skepticism. But it showed that there was something potentially interesting here. So we started to think a little bit more seriously about, can the technology be used in diagnostic applications? And that got us thinking about, well, what are the problems that actually need to be solved here? One of the most striking statistics I think I've ever seen is this one, that 1 in 2 of us are going to get cancer, from parents, grandparents, children, grandchildren. 1 in 2 are going to get cancer. And when you look across different types of cancer, it's very uneven in terms of the survival chances. So some, screening tests are pretty effective. Treatments are effective. For other diseases like colon and lung cancer, they affect an enormous amount of people. A lot of people get the disease. And actually the survival chances haven't improved very dramatically in the last 40 years. In lung, it's barely changed at all. And the crazy thing is, we know what to do already. So we know today, with treatments we have today, if you pick up a cancer at stage 1, survival chances are about 90%. And if you pick it up at stage 4, that drops to about 5%. So you've got to be pretty lucky to be in that 5%. So here, we know the problem. We kind of know the solution. So if there's a single lever you can pull in the war on cancer, it would be to pick it up sooner. So in 2012, 415,000 people were diagnosed with colon cancer. One was my wife, Kate. So this is our wedding day. 3 months before this, she was rushed to hospital in Addenbrooke's. She'd been told that she had IBS and stuff before that. And they're like, actually, you've got colon cancer and it's spread. And she wasn't one of the lucky ones. And obviously, since then, through then, I've been sad and angry. But it's not just about our family. It's the story is not unique. Millions of people have the same story. And I'm sure many of you, who here has lost someone in their family because of cancer and late diagnosis? So practically everyone. So I think we can use this anger as an energy to try and do something about it. And when you look at colon cancer, so again, it's the second biggest cancer killer. And in this case, there is actually tests today that can pick it up sooner. But too many people are still diagnosed too late. So the question is, what's going on? Why is it not working properly? And a lot of it has to do with the nature of the test itself. So if you think of colon cancer screening, the tests are either a fecal-based test or a colonoscopy. And the reality is people don't like them. And because they don't like them, they don't show up for the test. So if you look across Europe, compliance rates are about 50%. So half of people don't show up for the test even though the test exists. The second thing is the test isn't very good for the fecal-based test. So if you had 100 people that have colon cancer, half don't show up, they're going to develop late-stage disease. The half that do show up, the sensitivity is not very good. You only pick up about 2/3. So the sensitivity is the ability to see the cancer when it's actually present. So it's these two factors combined, which are the heart of the issue. You need to have tests which are acceptable to patients, but you obviously need to have tests that have the sensitivity, low false positive rates, and are economic for healthcare providers like the NHS. Now, obviously it needs to work as well. So has anyone ever come across cancer sniffing dogs? You kind of see them in the headlines every once in a while. Kind of New Scientist, BBC, it pops up, and you're kind of like, what's going on here? The interesting thing about a lot of these studies where the dogs will look at a urine sample primarily is that they're statistically quite robust. So when they train the dog and test the dog gets it right quite a lot of the time, much more so than would be by chance. So there's a kind of underpinning process here that we don't quite understand yet, but some evidence around this and some evidence that's been coming through the research community using conventional lab-based instruments as well to try and look at some of these chemical biomarkers of disease. And what we know is whenever you breathe out, objectively there's thousands of chemicals on your breath. And these chemicals are VOCs, volatile organic chemicals. And we think some of these are biomarkers in different diseases. And the two obvious questions are, what are they, where do they come from? And so some of the compounds are volatile metabolites, chemicals produced in the body that come from blood into the airway and out onto the breath. And these are, again, some of these are candidate biomarkers in different diseases. And others come from outside of the body. They're exogenous. They can come into the body and then are excreted out again. So this can be things like air pollution, carcinogens, things that are actually disease-causing. But actually, we can also think about how we can use this approach to try and probe for cancer as well. I'll touch on that in a little bit more detail. So there's chemicals in the breath. Some are produced within the body. We know that a breath test would solve the compliance issue in cancer. But why do we think there should be a robust set of VOCs associated with early cancer detection? And part of it comes down to existing tests. So if you're familiar with things like a PET scan, where you'll take a substrate, go into the scanner, and the tumor is then visible within the scan, that's because of the altered metabolism of the tumor. We've known for a long time that cancer has an altered metabolism. So we can start to look at that principle and say, can we figure out the chemicals that are produced or modified as a consequence of that? But there's a second important aspect about PET scans as well, which is that we've introduced a compound into the body to help us see the signal there. And that's a useful analogy when you start to think, can we deploy something similarly within a breath test? So this is a busy slide. So I want to give two analogies here. So the way we're trying to think about this is trying to understand how these chemicals are modified by the tumor, understand what they are, and see if we can pick these up on breath. So my analogy is a bit like if your car engine is a bit buggered, you can see some differences coming out in the exhaust. So it's just relying on something has changed and looking for some of the output of that. The other way in which you can approach it is, again, taking this probe type concept. So one of the techniques that we've developed is called exogenous VOC probes or VOC probes. And here the principle is a chemical goes into the body. It's a unique chemical. You can put it in a quite high concentration. And you exploit features which are specific to the tumor. So within the tumor microenvironment. You can have some specific enzymes that will allow the production of a very unique compound, which is then excreted on breath. And there's been some wonderful work done here looking in mouse models that showed the production of D5-ethanol in mice that have tumors that are as completely unique property of the tumor microenvironment here. So what we're trying to do is tackle the problem from both ends, to try and say, is there things that we can see which are a little bit different about the tumor and the chemicals which are produced? And can we figure out specific compounds introduced into the body that will help light up the tumor, if you like, but rather than putting someone in the scanner, you can look for the chemicals that come out on breath. The other kind of unique aspect of breath as well, it's obviously non-invasive. And when you look, where do the chemicals come from? Some are produced locally in the airways. And this is great when you're thinking about respiratory disease. And we do a lot of work in precision medicine as well. But most of it originates from the blood. And that makes sense. You know, your lungs are designed to exchange gases from blood to the airways. But one of the really nice things that you can do is with each exhalation, you have these chemicals coming from blood into the airways. What you can do is trap and store and enrich your sample over time. So with each exhalation, you're building up more and more concentration of the chemicals derived from the blood. And this is quite unique because I can't turn around and say, please can I have 10 liters of urine? Or please can I have all the blood in your body to try and find biomarkers? But I can say, why don't you breathe normally for 5 minutes as we enrich the biomarkers originating from the blood coming out onto the breath. That's only the volatile ones, you don't get the non-volatile, so that's the big limitation there. But I think this is a very unique advantage. So I think these factors combined are quite powerful when you're trying to see if the technique can be applied in the cancer detection arena. So this all sounds brilliant. You know, non-invasive, you know, there may be biomarkers here. You know, because we were coming from a very different perspective, you know, we were doing the sensor work where you knew the compound you're looking for. We actually had a bit of time to try and understand, you know, where are all the breath tests if this is so great? And actually, you know, there's tons of papers that have been published. And all the papers say, breath testing started in 1971 when Linus Pauling blew into a mass spec. I'm like, you know, that was a while ago. You know, where are all the tests? And I think what we observed was that often people were worried about the wrong problem. So often people were trying to develop the best sensor you could. But actually, the problem wasn't necessarily the sensor. The problem was, how do you get a good sample? So if you think about blood-based analysis, for instance, you know, if you don't get a good blood sample, you're not going to get the right answer, and the same is true in breath. So actually, there's some fundamental technology challenges that need to be addressed there. I think one of the other big things that we saw was that often there'd be quite small studies that weren't sufficiently powered, and you know, the findings were never taken forward and validated in bigger populations. So I think there was lots of issues that we saw that we wanted to try and systematically tackle and think about it from a systems perspective, because it wasn't about one piece or another piece, it was about how the whole thing comes together end to end. So the way to think about it, the way we think about it, is breaking the problem into the two constituent pieces. How do we collect samples, and then how do we analyze those samples? And this bit had been largely neglected. So what the team here, and there's a bunch of them in the room now, again, all I have to do is go and raise the investment. These guys need to make the thing actually work. Developed a device called the receiver, which is one of the constituent parts of the Breath Biopsy platform. And the receiver device basically allows you to capture all of these chemicals, or as close to all as possible, coming from the breath, and store them in a cartridge in a very stable way. So it's a bit like a sponge. The chemicals from the breath come out, stick to this sponge material. And once it's in there, it's very stable. So this cartridge can then be sent to a lab for analysis. So this allows you to do things like, collect lots of chemicals, but also enrich the sample over time, which is again one of the key ways in which we can try and get better sensitivity in everything that we're trying to do. Now, here was one of the other problems that we came across quite early. So, remember the sensor technology, one of the things that's special about it is you can say, I want to detect chemical XYZ, and I can program that into the chip. So if you looked at breath compounds like acetone or isoprene, we were thinking, okay, you can program those in. And because a lot of work had been published before, we thought all we need to do is go to the papers that say the biomarkers for lung cancer are XYZ and program that into the chip. But as I kind of mentioned earlier, that wasn't that straightforward. We would trawl all the literature. Nothing agreed. So we would not find papers that said, yes, the biomarker is this for lung cancer, and it shows up in 20 papers. Paper 1 would be like the biomarkers X. Paper 2 would say something different. Paper 3 would say the first two guys were idiots. They don't know what the fuck they're doing. So I think this, for us, changed the focus of the problem that needed to be solved. The problem wasn't just trying to pick out a set number of chemicals. The problem was trying to find the biomarkers, full stop. And that is where the field kind of is today. That's what we as a field and what we're trying to do at Owlstone is trying to solve that problem. So that meant that actually what we were trying to do on the analysis side of things, once you get your sample back to the lab, we had our chip technology, but that can't do anything unless you tell it what to sniff. And we needed to do this discovery work. So that meant we had to invest millions in building out a breath biopsy lab using high-end mass spectrometry, and we've entered into a partnership with Thermo. But these are the types of things that we didn't know at the outset. And it's as we kind of moved step by step along and found out more, we'd find more problems. And it's like, actually, we need to do something slightly differently to try and tackle this problem that we didn't know about this time last year. So I think at the moment, the name of the game is really about trying to identify and validate these biomarkers. And once that's done, actually, we have the technology and the ability to take that through into a test. And that's the kind of last piece of the puzzle, I think, because you have you need to do larger scale studies. So we've been very fortunate with some of the partnerships that we have. Some of the original funding we got was through SBRI from the NHS. And we've partnered with CREK here in Cambridge, running studies in different cancer types like lung, liver cancer, upper GI cancer. And I think here, when we go into these types of studies, there's no guarantee of success at all. Like, this is the hardest problem. Of the different things that we could try to do in breath, this is the hardest one. This is the one that does have a high chance of not working. But our belief is we have to try. The problem needs to be solved. And I think what is quite encouraging at the moment is the amount of money that's going into trying to solve the early detection problem in cancer. We are pursuing the Breath VOC route. Others are looking at circulating tumor DNA, other blood-based biomarkers as well. Someone just needs to solve the problem. And I think that that's the key. We mustn't lose sight of the fact that we just need to pick up cancer sooner, because that will be the transformative thing that saves lives. We've just quite recently started to get data back from some of these studies, which has been very encouraging, which is suggesting that there are biomarkers through these evoked probes that can certainly be relevant when you're starting to think about liver disease, and time will tell to see if we can translate these through into early cancer detection. So I think, going back earlier to the point that I was trying to make, that you only ever see the kind of polished version of what the company is and what it's done. in my view, no matter where you are, there's the kind of shit that you've had to wade through to get to this point. But there's always going to be shit that you need to wade through getting into the future. And that is just a fundamental reality of startup life and building and running companies. But I think, again, keeping the end in sight is the key. There's a lot of problems where, again, these problems just need to be solved, and we just have to keep plugging away. But one of the things that we realized was, yes, this is a problem that we should try to solve. But if you think about placing a bet, let's say place a bet, there's a 90% chance that you'll double your money, right? That's a bet that you should place. You're going to win overall. But if I said to you, every penny that you have in the world, you need to place on that bet. You can't do anything less than that. Would you do it? Probably not. Because even though odds on you're going to win, there's still a chance that you might lose and lose everything. And I think within companies, there's always that little bit of, how much do you go all in on one thing versus, how do you spread the bets a little bit? And I think what we were trying to do was make sure that we weren't afraid to take the risks in trying to do the hard things like early cancer detection. And because we'd built a lot of the elements, Simon, wave Simon, there you are. Because we had built a lot of the elements of the Breath Biopsy platform for our use, for our trials, collection, labs, what we realized was that this is also of relevance and interest to research customers. So academic institutes, pharmaceutical companies who are trying to find biomarkers to detect disease earlier or to try and find biomarkers that predict whether or not patients will respond to particular therapies. So what we started to do was build out a research products and services business as well to help reduce our downside risk a little bit. So you have some money coming into the business, but also we have clinical partners coming with problems that they know a huge amount about, who are funding research and using the technology to try and find potential biomarkers for their application. And if they're successful, that's going to help us as well because we can then take those through into additional breath biopsy tests. So I think a key thing that we've tried to do here, it goes back to the business model again, trying to think a little bit about how we have a business model that allows us to take risks, but not in a way that completely exposes the business if one trial doesn't go the way that we should. And over the last 18 months or so, 2 years, we've been fortunate. We've got a lot of clients, here in Cambridge, but like the Mayo Clinic, Cleveland Clinic, and pharmaceutical companies like AstraZeneca, GSK, and J&J as well. So I think if I look ahead a few years, we'll start to see more and more biomarkers coming out from these types of studies, in addition to the work that we're trying to do on the cancer side of things. And our hope is ultimately we can add breath as a new diagnostic modality that sits alongside and complements what you can do in blood and urine-based analysis. It won't completely replace these things. I think it's about how clinicians can use combinations of tests together to get better, a better sense fundamentally of what's going on with patients. And I think we want to be the leader in breath as this new diagnostic category. So, bunch of papers have been published, a bunch of studies which are ongoing at the moment. So there's been over 100 papers and posters which are up on our website now. So I'm pretty optimistic that in the future, and it won't be the near term, this isn't 6 months, 1 year, this is over a longer period of time, that we will have tests which patients aren't afraid to take because it is literally just blown into a device. which will have very robust biomarkers that help pick up disease sooner and helps guide patients onto the right therapies. And here's just a couple of examples of where these have been published, looking at pancreatic cancer and esophageal cancer as well. So, we've built this underpinning technology, and the evidence base is building and will continue to build over time. So when my wife Kate was sick, she wrote a book. She was a high achiever. So she's on chemotherapy, and she wrote a wonderful little book called Late Fragments. You go buy it. It's worth a read. And in it is one of my favorite quotes here, which is, make use of time while it's present with you. Depends upon your will, not upon the number of days that have sufficient length of time. And I think for me, Kate, her book, words like this are a reminder of what we should be doing. And I think it's one of the wonderful things about Cambridge, actually, with the amount of startups and people trying to solve the problems of the world, and climate change, healthcare, you name it. Cambridge makes a difference day in, day out in these types of challenges. So I think this is something always to keep it front of mind and never to forget. And I want to do one last plug, because Make Space is phenomenal. I think, again, it's one of the things that makes Cambridge very special. And recently I met a guy called William Wassa, who lives in Uganda. And William, I got to know him through the Royal Academy of Engineering, who ran a program trying to promote young engineers in Africa to try and solve problems that they were facing every day. William, I think, is a genius. So this guy has developed a system for smear tests where he's built very low-cost microscopy system and very sophisticated back-end AI to try and train and spot anomalous samples. And he did it all himself, one person. But coming through the Royal Academy of Engineering, one of the things that he's trying to do now is connect with very bright, very motivated, very committed engineers, scientists, data scientists, AI experts, doctors, physicians, to try and help push this further along, to try and make a device that can genuinely be deployed locally within his country. So the ask I will make is, any of you wonderful Make Spacers that want to make some time for William to help him move this along, please do chat to me afterwards, because I think this is a guy that is going to change a lot of people's lives for the better. So thank you, love that. Questions? Do we do questions on it?
We weren't going to do questions, but unless you want to.
Well, I'm happy to answer any questions, but thank you so much for the time. Really appreciate being here.